Deep in the universe, astronomers are finding colossal formations of galaxies that challenge the standard model of cosmology. While matter should be relatively evenly distributed across the cosmos, we are mapping structures that exceed the theoretical size limits of our universe. This map shows two of those anomalies, the Big Ring and the Giant Arc. Standard physics dictates a strict size limit for galactic structures, 1.2 billion light-years across. The Big Ring spans 1.3 billion. The Giant Arc stretches 3.3 billion. They occupy the same slice of deep space, organized on a scale that shouldn't be possible. The discrepancies reach all the way down to Earth. Inside this massive concrete vacuum tube at the LIGO Observatory, highly sensitive gravity detectors have picked up inexplicable ghost signals, correlated high-frequency noise striking different facilities simultaneously. Standard cosmology cannot explain how these structures formed or why gravity detectors would register these simultaneous impacts. These anomalies suggest a causal link to events occurring before our current spacetime began. To understand this mystery, we have to look at a fundamental thermodynamic flaw in the Big Bang model. The second law of thermodynamics requires the entropy, or disorder, of a closed system to increase over time. Running the clock backward implies our universe started in a state of extreme, almost perfect macroscopic order. Roger Penrose calculated the odds of our universe originating in such a perfectly ordered state by chance. The resulting improbability is 1 in 10 to the power of 10 to the power of 123. Among all conceivable initial states, the configuration required to produce our universe is an infinitesimally tiny fraction of the possibilities. To resolve this mathematical imbalance, Penrose developed conformal cyclic cosmology, or CCC. This framework removes the concept of a singular cosmic beginning. In this model, cosmic history is an infinite sequence of repeating cycles, or eons. We are simply living in the latest iteration of an eternal process. If we fast-forward our timeline a Google years into the future, the universe reaches a state known as heat death. Over immense timescales, all supermassive black holes will slowly boil away via Hawking radiation, as all remaining physical matter degrades. The universe is left devoid of mass, populated exclusively by massless particles like photons and gravitons. This grid represents that empty future space. Massless particles travel only along light paths. Without matter as a physical clock, space-time loses its scale entirely. Lacking scale, conformal mathematics take over. The infinitely cold future expanse is mathematically compressed, matching a hot, dense singularity. In this geometric loop, the extreme heat death of one eon becomes the Big Bang of the next. Connecting two universes requires a specific physical bridge. Penrose and Christoph Meissner identified this as the gravitational wave epoch. As the previous universe ends, evaporating black holes floods the cosmos with gravitational waves. This graviton-dominated phase behaves like a classical gas, allowing total mass energy to be conserved as it crosses the conformal boundary into the new eon. Because this energy survives the crossover, violent events from the dead universe are expected to leave physical, detectable scars in our current reality. This is the Planck satellite, used to map the earliest light of our universe, the cosmic microwave background. Penrose and his team scan these maps for predicted imprints of the previous eon, low-variance circular rings and isolated hotspots called Hawking points. When a supermassive black hole from the previous eon evaporated, its final burst of energy expanded into our early universe. The temperature spikes of these Hawking spots are determined by the mass of galactic clusters from the previous eon. This transfer of curvature provides a potential origin for the structures we see today. The Giant Arc and the Big Ring may be structural fossils inherited across the boundary. Penrose even proposes that dark matter consists of arabons, ultra-heavy particles created at the crossover. Their decay would produce high-frequency gravitational wave bursts, matching the correlated noise detected by LIGO. This framework connects the largest galactic structures to the smallest signals in our gravity detectors within a single predictive model. The theory faces severe resistance. For the conformal boundary to work, all mass must disappear in the extreme future. This requires the electron to eventually decay, a phenomenon never observed and not permitted by the standard model. Critics also argue that Hawking radiation transfers too much entropy into the next eon, which would fail to explain the low entropy state required for our universe's start. We are left weighing a profound question. Is our reality a one-time miracle emerging from nothing, or is it part of a cosmic recycling program? Next-generation observatories may eventually verify these ancient cosmic scars, or falsify the theory. Regardless, conformal cyclic cosmology forces us to reconsider the nature of time itself, suggesting that every ending is simply a catalyst for a new beginning.